So, welcome back, College Chemistry. We have been looking at how we can start to describe the change of our energies, both in reactions and for physical objects when we're looking at our Q equals mc delta T, our calorimetry. But today we're going to actually be looking specifically at the energy required to start to change our phases. When we're looking at a substance and actually changing it from a liquid to a solid, or a solid to a liquid, liquid to gas, gas to liquid, all that stuff. And so when we're going to look at these, we oftentimes will graph the data that we've collected over the course of the phase changes in what's called a heating or cooling curve. In this case, we've got a heating curve example. You'll notice we started way down here at 0 degrees. We started cold, and we started as a solid ice. In this example, we're working just with water because it's a nice kind of standardized graph for us to look at. And we started heating it up. And you know what's going to happen if you heat up ice, right? We take some external heat energy from the surroundings, we put it into the system, and our particles absorb that heat. The heat is entering for all of our phases here today, for all of our kind of different parts and pieces. All of our energy is going into the system. So all of these are going to be endothermic. We're going to end up with some final substance that has more energy than what we started with. And so we started actually way below freezing point. So this is in Kelvin. We started at theoretically absolute zero. Not a thing we can do, but we're going to pretend. And so we started real cold. And so at that point, we took our solid ice and we started putting heat in. Putting heat in, putting heat in, putting heat in. And what happened was our solid particles start moving faster and faster and faster and faster and faster. We see the temperature increase. Remember that the temperature is a measure of the average kinetic energy, the energy of motion. And so you'll notice there's kind of three regions where the temperature is changing. And this is where we're in the same phase. Here we're in the solid phase, here we're in the liquid phase, and then finally we've got our kind of trapped container of gaseous particles, gas phase. And so anywhere where the temperature is actually changing, that means you're putting heat in, the particles are actually moving faster and faster and faster and faster and faster. And so if we want to know the amount of heat energy that's entered at that point, we can actually calculate that using our calorimetry, our Q equals mc delta T. Remember, C is our specific heat. And for our specific substance, for our water, our ice, and our steam, we've got some C values for those. Now notice that they're different. And this depends on how the particles are arranged and how well they're going to transmit that and absorb that heat energy. And so you do need to watch out for which substance you're going to use or which substance you're at and which specific heat you're going to use. I'm going to look at some examples here. Don't worry, I'm just kind of talking through the general trend of the graph. And so we've got some specific heats. And so for any time, I'm going to just be here for just a second. So for any time you're actually changing temperature, we're going to use Q equals mc delta T. So for our solid phase, we'd use that. For our liquid phase, we would use that. And for our gaseous phase, we would use that. Just keeping in mind, kind of the caveat, we got to make sure we're using the correct specific heat based on the phase that we're in, because it's going to vary across the board here. Cool, but there's a problem, because when we're melting stuff, there's this point in which it flatlines. You'll notice there's kind of two regions on the graph here where we know heat's still going in. We know that the heat's still going into the system, but we no longer register a temperature change. That's because we're not using our kinetic energy. We're actually using this energy to overcome or break our intermolecular forces. We're breaking our solid particles away from one another. They're becoming liquid, fluid. And so we'd have to do something different. And there's kind of a key or a kind of a clue you can use here. And that's in our units. And so when we're actually changing from a solid to a liquid or a liquid to a solid, we use what's called the heat of fusion, the heat of fusion. You're fusing for a solid, you're fusing things together if you're forming a solid. So that's where that term fusion comes from. And so if we were going to try to figure out how much energy actually entered the system in order for this particular example, in order for this phase change to occur, how much heat entered the system, we would actually have to use a different formula because we don't have a temperature change. Our delta T would end up being 0, and we would say, oh, Q equals 0. There was no heat that actually went in here. Well, that's not true. We know that heat went in, we just used it differently. And so we would actually just look at our units. It's for our heat of fusion, change of heat of fusion, it is 334 joules per gram. Oh, okay. So if you want to know your delta H of fusion, you're just going to go ahead and take your mass, your grams, times that delta H of fusion. Ooh, sorry, I should, oh, not that button. Because we're solving for the heat here. So if we want to solve for the, oh, come on. Sorry, technical difficulties. If we want to solve for the Q, the amount of heat energy that actually entered the system during that solid phase change or liquid melting phase change, excuse me, we would take our delta H of fusion and we would multiply by the mass. Because we want to know how much energy is it going to take to melt however big a block of ice we happen to have. Because if the block of ice was bigger, it would take more ice or more heat energy to get it to all liquefy. And so we would just multiply those together. Up here for the boiling phase, for our heat of vaporization, we're making a vapor. Our Q here would just equal our delta H of vaporization, again, times the mass. Again, times the mass. Cool. So there's two types of calculations here that you could see. If the temperature is changing, you're going to use that Q equals MC delta T. If the temperature is staying the same, you're going to have to use one of these either fusion or vaporization values, and you would just multiply by the mass. Now, the tricky part is if we wanted to know, okay, what was the total heat energy that went into this system to get us from 0 degrees, or excuse me, 0 Kelvin all the way up to our final temperature, well, we would have to incorporate every single part of our graph. And so we would actually end up solving for 5 different, 5 different Q values. And then in this case, we would add them all together. And this is the total energy that we put into the system. It would be a positive Q value because we know we heated the heck out of our ice to get it to turn all the way into this superheated steam. Cool, let's take a look at an example here. I just want to make sure we've got some good solid examples, but it's nice to talk through the general graph and think about what it is we're looking at here. I'm gonna jump down real quick to number 5. I want to look at a couple of example problems on number 5 here, just to make sure we are feeling comfortable. Cool. So let's try number 5. 5 says you've got a 20.0 gram sample of ice at 50.0 degrees Celsius, negative 50. How much energy is required to ... Oh, okay, well, we're going to need a couple data points. Real quick, I'm going to jot down some of our values here so we've got those handy for us to use. Give me 1 second. I'll be right back. All right, so I've got my constants jotted down. If you need reference to those, remember they are right there on that front of that handout for you. So if we're looking at number 5, so just for part A, we're saying we're going to heat the ice to 0 degrees Celsius. Well, if we're just thinking about our graph, our heating and cooling curve, we're starting cold and we're heating it up. Boop. So we're really just interested in that first kind of temperature change because we're going to heat it up to 0. And at 0, we're going to see it start to flatline again. So here we would actually change in temperature. Q equals MC delta T. We just need to make sure we've got the right specific heat value. So trying to figure out our Q, our mass was 20.0 grams. For our solid, for C for ice, our C value was 2.060 joules per gram degree Celsius. And now we need the change in temperature. So delta, that's final minus initial. Well, our final temperature here is going to be 0.0. Our initial, so minus our initial, which was negative 50.0, and this was degrees Celsius. Check your units, grams cancel, Celsius cancels. Negative minus a negative, subtracting by a negative is going to give us a positive. So we can go ahead and plug all this in. Let me grab my handy dandy calculator here. 20.0 times 2.06. I'm going to go ahead and then take that times, well, in this case, it'd be 50. So looks like I got 3 sig figs, cool. So when it's all said and done, I got 2060 for my Q. Q is, again, heat energy, so this would be joules. I think was the only unit that didn't cancel from our first equation. Cool, so now we know in order to get our 20 grams to heat up to 0 degrees from negative 50, it's going to take 2060 joules. B says we're going to melt the ice. Okay, back to our table here. If we're thinking about our graph, we've already heated it up to the melting point, and now we're going to, oh, nope, don't want that. Now we're going to start to melt it. So here we don't have a temperature change. So if we want to solve for Q here, it's going to be delta H of fusion times our mass times our mass. So our delta H of fusion for our ice value, and again, this is going to be specific to the substance you're working with. We would not expect you to memorize these. These values will be provided for you. You just need to know what to do with them. And that's joules per gram. That joules per gram gives us a hint that we just need to multiply by the mass. In this case, it was the 20.0 grams. All right, so 334 times 20. 3 significant figures. Looks like we've got, for this part, Q equals 6,680 joules of energy. Box my answers here because I'm going to need those here in just a little bit. Keep in mind that we are melting. As we are melting, we should have positive Q values because we're putting heat energy into the system. The good news is your delta T will take care of this for you. If you have a final minus initial that comes out to be negative, well, then your whole Q comes out to be negative. The only time you got to be watching out for that is if you are melting or freezing. If this was the reverse, if we were actually freezing this ice, nothing in the math here would have indicated to us that, oh, wait, this is the amount of energy we're actually taking out. So be careful there, thinking about which direction your energies are going when you're actually running your math. The flat lines here, we actually have to make sure we're putting the right signs on them based upon whether we're freezing or melting. For melting, we're heating it up, we're putting heat energy in. That's an endothermic process. Cool, so now we're in the liquid phase. We've got our water. And so we've, back to our pen. We've heated up the ice, we've melted all of the ice, and now we're heating up the water. So we're in this region of our graph now. We're back to a temperature change. Q equals MC delta T. Mass is, so we're solving for Q again. Our mass is still 20.0 grams. We need specific heat now for the liquid water phase, which is our 4.180 joules per gram degree Celsius. And change in temperature here. Well, we started at 0, we ended at 100. Final minus initial would be 100. Final minus initial. Did I do the first one wrong? Wait a minute. No, final temp was 0. Yeah, no, okay. Nope, sorry. Final temperature here is 100, yes. Heated up to 100 degrees Celsius. We started initially at 0. So it's going to be a positive 100 degrees. 100 times 4.18 times 20.0 gives us a final Q for this liquid phase. Ooh, am I going to have enough room? I'm going to sneak it in there. Hopefully we can get in there. I've got 8,443.6 with 2 significant figures is 8,440 joules. Ooh, that's a lot of energy. Oh, it's like it's a lot of ice and now liquid water that we're heating up. Cool. Now we need to boil our water. We need to boil. So we've melted, we heated up our ice, we've melted, we've heated up our water, and now we're gonna boil. We're flatlined again, So now we're trying to solve for our Q. It's gonna be delta H of vaporization, again, times the mass, times our mass. Back to our handy constant sheet for delta H of vaporization. For water, we've got 2260. Oh my goodness, that's so much bigger. Oh, it's almost like we're going from some attractive forces to no attractive forces. Remember, for a gas, you've got to get all the attractions to break so that all the particles are now floating freely away from each other, times our original 20.0 grams. Go ahead and multiply those. 2260 plus 20.0. Looks like 3 significant figures on this one again. I got 2280 joules of heat energy going into the system to get our water to all boil off. That's not right. I added. That's not right. Should be way bigger than that. 2260 times 20. There we go. That's better. 4, 5. Come on, 5. 200 joules of energy. Yeah, it should be way bigger value. Glad we caught that when we were talking about that. Good. Now we got to heat up the steam. So if we're thinking about a graph, we are at that very last tail end of our phase diagram. Heat up the steam, we got to change in temperature. So Q will equal MC delta T. Just keep in mind that C is going to change depending on how those particles are going to absorb that heat energy. Mass is still 20.0 grams, still the same mass of particles. C for steam, 2.020 joules joules per gram degree Celsius. Our final temp here is 125. Initially here, we were starting at 100.0 degrees Celsius. All right, we can solve for our temperature change here. It looks like 125 minus 100 is going to be 25 times 2.020. My decimal got a little faded there. Whoop. Make sure we got our right math here. Times our 20 degrees. We've got, for heating up that steam, looks like it's going to take us 1,010 joules worth of energy. Oh my goodness, we put a lot of heat energy in here. So F then asks, what is the total amount of energy needed to get from -50 all the way up to 125 degrees? Now I want to call out the most common mistake. Students will see this temperature change and go, oh, shoot, well, I can just do 1 Q equals MC delta T because I got 2 temperatures and just solve for the energy that way. Doesn't work. We have to incorporate the fact that the different phases absorb the heat energy differently, and that during the actual phase change, we actually have to put a bunch of energy in to get the phase changes to occur, for those intermolecular forces to break. And so you've got to incorporate all 5 of these steps if you're going to go all the way from a cold solid to a superheated gas. It's much more than what you want it, what you're expecting it to be, because we got to incorporate all those pieces. But the good news is, for a Q here, it's just the total of all of our Qs. Total of all of our Qs. We're just going to sum. We're going to add them all up. The tricky part here is going to be in our significant figures. So I'm going to go ahead. I'm just going to add them all up real quick. I'm going to add 2060 for part A plus 6680 from part B plus 8440 plus 45200 plus 1010. Enter, and I get. And I add up all of my answers from all 5 of my parts here. I get 63390 joules. But you know it's coming. Significant figures. This is tricky because we've done our multiplication, rounded for our sig figs. We got an answer for each part, so we would watch our sig figs there. Now we've added them, and when you add, you look at the decimal places. You can only be as precise as your least precise decimal place, and I think it's actually coming from part D. In part D, we didn't know what was in the ones place. We didn't know what was in the tens place. We only knew what was in the hundreds place. These 2 zeros are just placeholders telling us the thing we measured was really big, which means we have to round to that same place. We're going to have 634 and 20. Sorry, I said that wrong. 63,400 joules total. I know what you're saying. I don't like that. I don't like rounding off 90 joules worth of energy. That has to do with just how we actually measured our values here. If you want to be more precise, you need to get new tools that have more precision incorporated on them. If we were going the other way, if we had started hot and went cold, all of these values would have been negative. All of our answers would have been negative Qs because we'd be taking all of that heat energy out. Right? You put it in the freezer, and the freezer sucks all that heat energy out of the water. And so this would end up, they would all be negative values, and you'd have a great big negative Q value for part F. Cool. A lot to keep track of here. Always be looking out for those phase changes. Even if you're just changing a little bit, you might be changing across the phase change, and you still have to incorporate that into your equation. Cool. If you got questions, feel free to give us an email or come in and see us. We'll make sure we got you on point.